Yes. Welcome back. Do you realize I had an anxiety dream last night in which I overslept and I missed this class? I know, like how, I don't even think I'm capable of that anymore, but I'm so glad I didn't, because I would have felt really badly if everyone showed up, you know, in their snow boots and I wasn't here. So thank goodness that was just a dream. So yes, I posted a new homework, told you guys all about it, so that is due next Wednesday. After today, you will know everything you need to know to be able to do that. You know how to do the first section of it right now. We also have a quiz to go over, and we're getting towards the end of the semester. Believe it or not, 6 weeks I counted in terms of new material. I'm not done with the stuff for Thursday yet, but I hope to be tomorrow. And just so you know, we have, as I told you, we've finished everything that the old 6242 was going to cover, as well as intermediate statistics, by the way. I just did it in a different way than some of your friends are taking. And now we're into the correlation regression section of the program. So for those of you who have eyed that course, you won't need to take it because I'm doing all of that next. So that's multiple regression. So the quiz that we have for today, the formative assessment, I looked it over and we have some things to discuss. Things are going reasonably well, but a few common areas of misconception. But dialing it back a minute before we get into the specifics, let's remember, why are we here? What is this course about? And besides, it's a requirement and they made me. We'll just take that answer off the table. But what are we here for? Yeah, Tanya, what do you think you're here for?
Well, specifically to my department, I need to have an understanding of how to work data.
An understanding of how to work data, okay.
And then for my own benefit as an educator researcher, I don't know anything about math or numbers, so I am learning how to interpret data.
How to interpret data.
Excel charts instead of just going and reading the descriptions and
And skipping the numbers part, right? So yes, so stata being a practical skill. Another line on your CV of things that you have, technical skills as a section, yes. Interpreting data, right? So why are we learning statistics? What does it allow you to do as teachers, as educators, as researchers? What does it do? What's it for, besides scaring people? Right? Research, yeah, quantitative methods, right? It's the idea of answering questions with data. That's what we're here for. We have to be able to summarize data, to get the trends out of it, to get a sense of the certainty with which we have those trends, to be able to judge how it compares to other things. So I don't want you to lose sight of that big picture, right? All of the nuances you can come back and review if you understand where to look. So what have you learned how to do so far this semester? What do you know how to do now, albeit with some review or whatever you need for scaffolding that you didn't know how to do before?
I mean, I didn't even know like how to log into Citrix.
Yep.
Like I'm talking about, I didn't know about coding, talking to a program. I didn't know how to run in something that looks like DOS.
Oh, it gets worse. I could be teaching you R, and that like literally is a DOS window.
Yeah, I mean,
So
all sorts of things.
okay, so
Even
learning
that
how to
level.
use the packages. Now, why is that a valuable skill?
Well, so for me, I'm a qualitative researcher by being trained or whatever. But I think that I like the idea of being able to back up some of my not theory, not just some of the things I'm finding in the data through qualitative measures to back them up using quantitative measures.
Converging evidence, so
Yes,
to speak.
and that's really sexy to me. I think and it makes a lot of sense to me, so that's what I like.
Good. Yes, and being able to do it in a program means that you're not relying on hand calculations or other things that are sort of pedagogical tools but aren't really going to help you in the real world.
Right, and that's not something I would ever be able to do, without like taking every single class until I graduate with you. It's just not in my wheelhouse. So I think, this is good.
Good. So what kinds of questions have you learned how to answer with using the software? logging into the virtual machine, figuring out how to speak to the program in a language it understands. How about you, Danae? What have you learned to do that you didn't know how to do before?
I'm running blank, but I know
You-
we do.
Do you want to phone a friend?
To make graphs.
Make graphs? Yeah, like histograms maybe, scatter plots, those kinds of things. Yeah. Sorry, I'm taking my boots off. Just making it a little more comfy up here. You can't see my feet from where you are anyway. It's fine. It's fine. And I promise they don't stink too badly. Make graphs. Yes, that's always helpful for showing other people data. A picture's worth 1,000 words. How about you? What have you learned how to do?
How to make comparisons between categorical variables.
Yeah, how to compare group means. Yeah, so answer questions about whether groups differ in their mean values on some outcome. And what is that called when you describe it to people, by the way?
Oh, good enough.
Starts with an A. 3 words. Analysis of variance. Anova. Yes, that is what that is called. Yes. How about simpler stuff? How about descriptive statistics? To be able to summarize information. That's another thing. Answering questions about descriptive statistics, like whether your sample mean is different from your population mean or something like that. That was the very first thing that we learned. So I wanted to actually pull that back up, just this very briefly. This is the first test that we learned. You can put a Z or a T here, but the idea is that you have the thing you found minus the thing you expected divided by the standard error of the thing you found. So the t-test that we use, say, to test whether or not a group's mean is different than another mean, takes the same form. It's the slope, and then minus there's an implicit 0, because that's what we're testing the slope against, as to whether it's 0 divided by the standard error. So the t-test that you show up on the output is basically the same idea. What you have minus what you expected over your level of imprecision around what you found. Yeah. How about other kinds of associations? Can you answer questions about associations between variables? Sure.
Correlation?
That's one kind. So when would you use a correlation?
You have two variables and you want to know if they're related at all.
Let me reframe that. So there's different kinds of correlations. Let's say Pearson correlation. That was the first one. So what kind of variables is that situated for?
So like quantitative essentially.
Yeah, quantitative variables, or more specific, what kind of categorical?
Kinds that we code ourselves.
Yes, not where I was going. In your homework, binary, yeah. You can put in age group as a predictor of a quantitative outcome. You can put in a quantitative predictor as a quantitative outcome. Bivariate correlation summarizes those relationships. Spearmint was the other one. That's for ordinal or quantitative where you're worried about extreme values. What about two categorical? How would you test an association? Like the crosstab looking thing. Chi-square, yeah. So you've learned how to answer lots of questions so far. So you should feel good about that, right? Even if it's snowing, you can feel good about that. The snow's gone. I just looked out the window, so did anyone get excited about the snow? It was very pretty.
So pretty. I took like 100 pictures.
I took some videos too.
I was like driving down the street with my phone out of my. I was a dork. I'm not gonna lie.
Not on the roads and sidewalks. Okay.
Yeah, the pretty kind that doesn't interfere, right?
It's like, it doesn't affect my road
Yeah.
related things, so it's great.
Yeah. Yeah, for me it's always, do I have to scrape my car? Because then I get really cranky, right? But that's my favorite part about having a PhD is affording a garage.
Everything, nothing.
Can't go back now.
Yeah.
Like beautiful stuff.
All right, so more specific stuff that you've learned how to do. This is a review of the idea of putting in one predictor variable into a model, and it's also setting you up for your next homework. So first question on formative assessment number 5. Consider a general linear model with one predictor. So let me unpack that sentence. General linear model. When you say that, what does that mean? What have you sort of chosen if you've chosen that route? What kind of outcomes are predicted by general linear models? Quantitative. And what kind of distribution for their leftover residuals? Normal. Are the residuals supposed to be related to each other? Like, would people be more similar? No, they're supposed to be independent. So this is not what you would choose if your people are related, like kids nested in classrooms or occasions from the same person. Residuals are supposed to be normal, and there's one more thing we're choosing about them. It's the fancy H word. Homoscedasticity. And if I were to say that in plain English, plainer English as it were, not that, yes, so even is the picture. You want your residuals to be sort of even. A synonym for that, yes, but not where I was going. Constant, yeah, constant variance. So that's what we've selected. And if any of those things is not likely to be true, what do you do? So all of these things, residuals that are independent, normal, and with constant variance, that can be true whether or not you have a curvilinear effect. If you're modeling a linear effect, and it should be curvilinear, then that can induce problems. But if you've exhausted what you know how to do and those things aren't true, you need a new model, and you need a new class to learn it in. So just keep that in mind, that this is the point. But everything that you're learning this semester generalizes to those more complex models. It's all of this plus extra stuff. So that's where the extra classes comes in. So general linear models with a single predictor, a categorical variable with 4 categories. So the idea here is we're trying to differentiate sort of the predictor as a concept. Like if I have a 4-group variable, a variable with 4 categories, I'm thinking of that as like group. Like that's one thing in my head. But to be able to differentiate the means across the 4 groups, how many fixed effects, how many fixed slopes does that take? It takes 4 altogether, right? Because there's 4 means. One of them is going to be an intercept. That means I need 3 slopes. So the way that I would code that to be most direct is to make one of the groups the reference. That is the group in which the slope predictor variables are coded 0 for that group. And then it's a 1 to distinguish each of the other groups. So question 2 then related to that. How many possible mean differences are there across my 4 groups, and don't say 4? 6. Yeah, that one was a common point of misconception. There are 4 means, but there are 6 ways they can be different from each other. 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. I'm sure there's some like permutation rule I could have figured that out by, but math was a long time ago for me too. So I'm just going to count on my hands. So of those 6 possible differences, how many would be given directly by my model?
3.
It is 3. That's my 3 fixed slopes, right? Which ones that are is up to you. But it's whichever 3 go with your reference group. It's the reference versus each of the others are what the fixed slopes would give you directly. How do I get the other 3? Subtraction, linear combination. So it's the slopes minus each other. So the difference between, say, 1 and 4 minus the difference between 1 and 3 gives you the difference between 4 and 3. Now I could do that math on a calculator and get the right answer. What would be the rationale for getting the program to give it to me as opposed to just doing the math on a calculator?
It's a lot quicker.
Quicker, human error. And even if I were perfect, what else would I have to calculate myself to be able to make some sort of judgment about that difference? The thing next to it in the output, right? Not just the difference. P-value, where does P-value come from? F or T, where does, how do you get an F or a T?
T is more than single and F is more than multiple.
Right, what goes into T? You can get an R out of a T, but how do you make a T?
You have to minus estimate minus standard error.
Yeah, estimate over standard error. That's why. In addition to human error and taking less time, if you ask the program for any linear combination of slopes or intercepts, it also gives you a standard error for that combination. So you have the estimate and the standard error that gets you your T, that gets you your P, that gets you your answer. So that's why. And the reason that I wanted to ask these two questions in particular is because this is section 1 of your current homework. You have a 4-group example. So take these things and make Stata or SAS do it for you. That's your. So in order to be able to do that, we will example 5, part 1. That's the one that we did before that has low versus middle versus upper. I'm looking for you to be able to extrapolate that. Is that the right word? Like extend it? So this is my scaffolding. There's the ball in the air and you can knock it out of the park. Okay, so questions on either of those two concepts? All right, next one. So once again, single fixed slope for a single predictor. So this would be the case if you have just a linear relationship of a quantitative variable or just a binary variable in which there's only one difference, and so that's the only possibility. One slope covers it. What is the relationship between the T statistic for the significance of the slope and the F for the significance of the model? There's a real simple mathematical answer, and then I'm also looking for words to go with it. How does T relate to F in this case?
So T is for the slope, and F is for the model.
Right.
Unless that was just said in there.
That is true, but how do they relate to each other if you only have one slope and thus only one T?
This was Terry's question. F is the T.
Say it again?
Isn't F is in a single predictor? F is the T.
Close.
T squared.
T squared
T
is
squared.
F.
Yes.
Yeah.
Sorry.
So there's a 1-to-1 correspondence. Because T is in the scale of the original slope, whereas F is in the scale of squared. It's in a variance scale, so T squared is F. T squared is F. If you only have one fixed slope in the model. Yes, Tony? Yeah. T squared is F. That's the numerical answer. Now, what does that mean? It means that if you only have one slope in the model, that slope is the model. So the significance of T is answering the same question as to whether that slope significantly reduces variance, which is what F is testing. It's the same question answered in a different metric. The original metric, which is T, and then the squared metric, which is F. Now, when will those things not be one and the same? Multiple slopes, exactly. Then we have a different question. We want to know if the set of slopes is responsible for a reduction in variance that's significant. So T squared is no longer equivalent to the F that we get for the model in that case. And what instances have we seen so far where we have multiple fixed slopes for a single predictor?
Like when we do the low versus LVM,
Yes.
MVU, those ones.
Yes, when we have a grouping variable with more than two groups, that's one situation. How about quantitative variables? We looked at a couple examples, and we're going to do that today too. Quantitative variables with what kind of relationship to y? What do you think? Quantitative variables, if I just have a linear relationship, that's one slope, right? So when would I want more than one slope for one quantitative predictor?
Piecewise ones.
Yeah, piecewise ones, quadratic ones, anytime you need, it's some kind of nonlinearity where you need more than one slope to capture that trend. That's the same idea as having a grouping variable that has 3 or more groups. We need more than one slope to capture the whole entity of the variable. In that case, the F for the model is not going to be just the same as t because there's multiple t's. And then related to that, so those are the significance tests. So if I ask a question in your homework, give me the test statistic for, you know that's going to be one of four things. That's a t, a z, an f, or a chi-square. And it's probably just going to be t or f from now on. In this class, anyway. In other classes, you'll get z's and chi-squares mixed in there sometimes too. The effect size then for the slope. You can do effect sizes for single slopes as r's or d's. You can get those out of the t's. That gives you a sense of sort of a standardized effect for it. So in a single predictor model, what is the relationship between an r effect size for the slope and the r squared for the model? Now this one, don't think too hard. What's the relationship between r and r squared? Squared. Yes, that is correct. So in a single predictor model, the standardized slope that you can compute, that's when you have the x and the y in a z-score metric, mean 0, variance 1. That is the same thing as Pearson's correlation, and you take that Pearson's correlation and square it, that is the model's r-square. So it's a one-to-one correspondence between the slope and the model if there's only one slope. Now, what is r-square? Last question. If I said I have an r-square of 0.12, what's that mean?
The correlation between predicted y and actual y.
The squared correlation, but yep. That's one way to say it. The squared correlation between predicted y, which is labeled what in notation? Y. Yeah, y hat sub I. Nailed it. And actual y, that's just regular y sub I, right? So it's the squared correlation between those two. Say it in terms of variance. That's the other one.
Proportion reduction variance.
Yeah, the proportion reduction in variance. How do we know how much variance there was to begin with?
When we run the BO one, the empty one?
Empty model will give this to that. That's the starting point. So that helps to illustrate why the sums of squares table is the way it is. The starting point, if you don't know anything else about a person, what's your best guess for their outcome?
Mean.
The mean. So the deviation of each individual's value from the mean squared, summed up, divided by people, that is all the variance that there is. That's what the empty model gives you without predictors. That's what you get if you run just descriptives and you ask for the variance of the variable. It then gives you a quantity known as residual variance, which is left over. That's how much your model accounted for variation in y. And that one is given as the difference between the variance explained, is the predicted minus the mean. Variance left over is each one minus the predicted. So it takes that total deviation from y and mean y and carves it up into how much is known because of y hat and how much is still unknown, the difference between y hat and y. So hang on to that. So an r-square, if I had it at 0.12, so I could say 12% of the variance in this outcome is accounted for by my model. And my model means all the slopes put together. I could also say the square of the correlation between the predicted y and the real one is 0.12. I could say that as well. How do I know if 0.12 is good or good enough? It sounds like a lot, but it's like 10%. I mean, 12%, that's not all of it. How do I know if that's something worth writing about? A significance test. What's my significance test of my r-square? What letter?
D.
That's an effect size. That's an effect size that gives you a standardized mean difference, and so that would go with a fixed slope of a categorical variable most of the time. Another letter. Couple down in the alphabet. F. Our friend F. So we have an F test for the r-square. That's what F is for. Broadly construed, it's a ratio of what you know to what you don't, where each is weighted by how many slopes you had to get to know it versus how many that you could have used but you didn't yet. So that's that idea of weighting it by how many things you use, that's degrees of freedom. So we'll look at output that has all of those things today. All right, questions? So do you want to go back over the grouping example, the part one of this, the low, medium, upper? Would that be helpful? Yes? Okay, an emphatic yes from over here. Anyone else opposed? No one's opposed. See, even if you feel like you understand it, doesn't it feel good to like hear it again and be like, I got this? Yes. It's never a bad thing to be certain of what you know. So this is example 5. We did half of this, and we haven't done the second half, although we looked at the concepts and the pictures that go with it in the lecture slides. Okay. This is posted, if you're looking for it, let me see, where did I put that? It's posted on 10/15. So that's where that goes, and then the accompanying Stata and SAS files that go with it are then posted on 10/15 as well. Okay. So the data set for this, I think this is going to be your last one with this data set. I'm going to pick a new one for the next one. So say bye-bye to GSS. And predicting income, it's too depressing. So personal income in thousands is my outcome. I'm limiting my sample to people under 200,000 and under age 75. I have my class variable. So highlighting this here because you're going to have to do this. Okay. So this is where we're making contrasts for each class. Now I have 3 lines of code here because I have 3 classes. How many lines of code do I need for 4? 4, yes. So it looks a little bit different in Stata. The logic here is that it's like if the class is this one, then make these new variables and set them equal to these values. So in SAS, this do end is grouped together. Do is used whenever you have a whole host of things you want to do if a case meets this criteria. And then end is used to sort of shut off that do. So yeah.
I wonder if you set class 3 equals 1, will the SAS confuse it with the VSM equals 1?
No, so I did have a class 1, but there weren't very many people in it, so I made them all 2s. So I could simplify this example a little bit.
So SAS will identify if it's a label or it's a 1 or 0 or 1.
These are actual values, so it shows up in this aqua color if these are values. So it's still going to read the variable as the numbers that underlie the values. It's just that the labels you assign to it will show up in the output if you use class as a variable, for instance.
Can you explain this if class 3 equals 2?
Mm-hmm. So the name of my variable that I've created is class 3. That's existing in the data set. So it has possible values of class 2, 3, and 4. And so the original variable in the data set was 4 categories, and I wanted to simplify it for this example. So I turned it into a 3-category variable by assigning the 1s to be 2s, and otherwise the old one goes into class 3. So class 3 is the thing I'm starting with. These are what's known as conditional logic statements. So if I'm in a case where this person has a value of 2, then I want to make these new variables, and I want them to be set equal to these numbers. They're constants. So it's new variable equals, and then where either it's an old variable or a transformation or a constant. And so my name here, like I made this up because of the context of this example. Class 2 is low, class 3 is middle, and class 4 is upper. So when I make dummy coded variables like this, I usually have the 0 group versus the one that gets a 1. And so that way I know what the order is. So this to me is low versus middle, this is low versus upper. And I've chosen to make low the reference group, meaning that's who my intercept is going to represent. The intercept is the expected outcome when all the x's are 0. So I'm setting it up as low as my you are here reference for the model. It's what the intercept will give me. For each of these other ones, because I have 3 classes, I need 2 fixed slopes. the variables that are going to then multiply those slopes are being created here. So if it's class 3, then they get a 1 for this one, meaning they're the middle group. If it's class 4, that's the upper group, and they get a 1 here instead. So if I had 4 classes, like you have in your homework, how do I need to change this? You already told me I need 4 rows. How many, sort of this way, do I need? Columns, so to speak. I need 1 more. So it would be, this is 1 versus 2, this is 1 versus 3, or excuse me, in these, this is 2 versus 3, this is 2 versus 4. If I had another one, it would need to be here. So 3 slopes to separate 4 groups.
That's
So the one that I told you to make 0, the third variable would also be 0. And then if I had a class 5, that would pick up the 1 instead of this. Now, there is a shortcut in the software to do this for you, but I'm deliberately not showing it to you yet. So just know that if you have like 10 groups and you're like, oh God, I don't want to write all this out, you actually don't have to. The reason I'm showing this to you is because it aligns with the model exactly, and it's what's going on behind the scenes. But I want you to understand what it's doing before I let it do it for you, if that makes sense. So just know that it doesn't have to be quite this labor intensive. But there's additional complexities that go along with letting it do things for you that you can get into trouble if you don't know what it's doing under the hood. Okay, so in Stata, I'm doing the same thing, but because I don't know how to do multiple commands for the same if, I'm assuming that's a thing, but I haven't been able to figure it out. I did so more succinctly. So I started off by generating the 2 contrasts that I needed both to 0, and then I just turned the 1s to 1 instead. So in Stata, it's backwards. So it's the new variable and the value that it takes if the old variable, and it's equal because it's like setting it equal to, not assigning a 0. Assigning a 0 would be 1 equal. Evaluating a condition is equal. And it took me a while to get that right on the first try too. So if you want to try and generate these contrasts and put them in an email and say, did I get it right? I would be happy to look at it and say yes. Now, how do you know if you got it right? How will you know in practice? So section 1 here, so your 4 groups in your next homework is a study about mini golf training, also conducted at Midwestern Red State University, where all my research is done. So there's 4 groups. There is a control group, a new mini golf training group, a new regular golf training group, and a group that got both at the same time. And I told you to make the control group your reference. So some of these questions then are going to help know whether or not you got the right model. So if your model successfully differentiates all 4 means, you will have the right residual variance. If you have done so in a way that I asked you in terms of who is the reference, then you'll have the right intercept. So that right here, this check question right here, that's checking your coding. New question?
The report part?
Yeah, so these are numbers that are going to show up in your results section. Anything with a check is not. So some things, like I ask things just so that you know you're on the right track that you wouldn't necessarily put as a part of your report. They're few and far between, but I try to denote that. Okay. All right, so we put them, we make pictures. Here's my empty model. I don't think I asked for that this time because you've already gotten the hang of that. Here is the 3-group model in this example. So beta 0 is the intercept. We know that that is the expected outcome when all the predictors are 0. So that will be for your reference group. Each of the other betas are your fixed slopes that differentiate the alternative group from the reference group. So note the wording on that. It's differentiating the alternative group from the reference, meaning that if beta 1 is positive, the alternative group gets the higher value relative to the reference. If beta 1 were negative, the alternative group would be lower than the reference. So the coefficient describes how far off the alternative group is from the reference. And I'm going to ask you to be able to figure out how to get the mean for each group and the mean differences. So the logic behind the code is up here. To be able to get the mean for each group, it's going to start with the fixed intercept for everybody. So those 3 lines right here coordinate with that. So when you see intercept 1, it's saying, okay, I need 1 beta 0. And then the values for 0 and 1 that go after your predictors are the terms in the parentheses that multiply the betas. And they match your coding. They match. So I know that this is the mean for the low group because that is when both of my predictor variables are 0. I know the second line is going to give me the mean for the middle group because that is when the first predictor variable is 1, but the second is 0. And I know the third one is going to give me the mean for the upper group because that's when the second predictor is 1, but the first is 0. Now, which of these 3 numbers is already given on my output and I didn't need to ask for it again?
What's the low mean?
The low one. And you can tell that based on the pattern here. It's not a linear combination. It's only one thing. But sometimes it can be helpful to do it anyway, because that way all of your answers are in one spot and they're labeled for you. So if I didn't want to go to the trouble to write this out, where in my output would I have found the mean for low? Given my coding. Want to try again?
Me?
Yeah, you're smiling.
Oh, well, I mean, that's your...
You know the answer, or you're enjoying the dialogue, one of the two, right?
A little bit of both.
Yeah.
Right? The low mean is that's your intercept. That's your...
Yes, it is. So if we come down here, the intercept, that is your low mean. How do I know that? The definition of an intercept. The intercept is the expected outcome when all the predictors are 0. I made the predictors that way. Let me go back up here. The low group is when both predictors are 0. They are my intercept. That is what the intercept is giving me, is their mean specifically. Okay, does that make sense? So the other 2 means are linear combinations. Beta 0 plus beta 1, beta 0 plus beta 2. You'll need to write 1 more of these to get the extra group that's in your homework. Now the differences. With 3 groups, or categories, by the way, group and category are synonyms in my head. With 3 groups, there are 3 differences. Any difference that is relative to the reference is given by the model. So those 3 lines coordinate with those. So low versus middle, that is what beta 1 is telling you. It's not a linear combination, it's just one term, so that would show up on your output directly. Likewise, low versus upper is one term, shows up on your output directly. The missing one is the difference between the two. any difference that relates to the non-reference groups, any difference among the alternative groups is a linear combination that you have to ask for specifically. So in your case, how many more of these are you going to need to write? 2 more, because there's 3 differences of the 6 that you won't get.
Can I just go real quick? So that green dot plots unpack diagnostics.
Yes.
Is that supposed to be green, or are you doing that for us?
Both. It is supposed to be green because I turned it into a comment because it generates a whole bunch of crap that I didn't want to see. So if you uncomment it, it turns it back on. So this is my way of like putting it in the example so that you have it as a reference if you want to turn the plots on, but then you don't have to
take away
invoke
the
it.
asterisk.
Yeah, exactly.
Okay.
Take away the asterisk and the semicolon and move the semicolon, like just use that semicolon instead. Yeah, because this ends the font, right? Over.
I see.
Yeah. Yep.
And it has to be in the same thought as the rest of the line to work?
Yes, this command goes on the proc line. So yes, if I wanted to look at all the pictures, I would do this. You watching? Okay. And then it would turn ungreen, but this is a Word document, so that's not going to happen today. There.
Thank you.
Sure. So what the logic behind these implicit differences then is shown right here. It's how you got the mean for each group literally subtracted. So if you take, what you want to know is middle versus upper. If you take this line upper and subtract this line. So take the upper mean line and subtract from it the mid. Intercept 1 minus intercept 1 cancels. 0 minus 1 turns into a minus 1. 1 minus 0 turns into a 1. And you're left with that. In the instructions for the homework, I have noted that in terms of the versus, so I have a bunch of questions like the fixed slope for control versus mini golf, direction matters, the one before the versus gets the -1, and the one after gets the 1. Otherwise, you'll end up with the right estimate, but it will be the wrong sign.
Can you see that?
Yes. So the wording of the questions follows something versus something else. The thing that is before the versus gets the -1. The thing that is after gets the 1. If you get it backwards, you'll end up with the right estimate, but it will be the wrong sign.
When we do this homework, are we supposed to be doing the math, like, not the math, it's not, but like, are we doing the subtracting, or are we supposed to be finding these numbers within the output?
So this is why this is so cool. What you're doing is telling SAS, hey, go find out what these numbers are and plug them in to give me the answer. So you will get another table of numbers.
Okay, so this, I think I see it. Yep.
Yeah, so this is the table that shows up by default. And I have labeled these for you in this example as to what they mean. The table of numbers that you then requested separately via those 6 lines show up here. So it took the estimates and the standard errors and it did the math for you to spit out these requested quantities. Okay. And then Stata, folks, it looks almost identical. The difference is that you need plus signs in between your terms and asterisks to indicate the multiplication. So this looks much more like the actual equation does. And also consts instead of intercept. And on your output, the intercept is last instead of first. Because, you know, job security. Why not make it look the same as everyone else's? All right. In your homework, I'm also looking for you to be able to identify this pattern. So this is still example 5, page 4.
Okay, gotcha.
So in the write-up for this, which I did at the very end here, for instance, this is a very common way of reporting your results. So I'm looking for you to put the right letters in front of your numbers. Because I will have asked for all of the numbers and they will be pre-populated, but there's your form. So let's go over this. F is your test statistic for your R square, right? What are the things in parentheses?
Denominator degrees of freedom.
Denominator degrees of freedom is the second one. Numerator is the first. Where do they come from?
Spent in slopes.
Yes, spent in slopes is numerator. 731 is not spent, right? Left over. So that's going to be the number of fixed effects total subtracted from your end, because it counts the fixed intercept. Then we get the F value itself. MSE, what does that mean?
The leftover variance.
It is leftover variance, but what is it called on your output?
Mean square.
Mean square error, yes. P goes with the F, and then R square is the variance accounted for. Now the reason that we've picked those values specifically, by convention, not just me, this is like the world and how I learned it, is because those values allow you to reproduce the rest of the table. Those are the only things you need to know to fill in the rest of this if you wanted to. If you have the mean square error, and you have your degrees of freedom, and you have the original variance of the variable, you can get the rest of this. So that's just enough information to be able to do the rest. Okay. All right, so questions on that? Think you can do it? I think you can do it. Yes, you can. Don't give me that. Yes, you can. And you know what? If you run into problems, what should you do? Ask. Yes. Come sit in front of me and ask. Send me an email and ask. I'm also happy to meet via Zoom, like if it's a day where I'm hiding at home or something, that's fine too. So yeah, don't get too mad. Like try for a while, and if it's broken, ask for help, please. You know they pay me, right? Like 40% of my time is supposed to be spent teaching. I'll be honest with you, it's like 80% right now because these are 2 new classes I'm prepping at the same time, but they're still paying me to do it, so that's what I'm doing. All right. So the other parts of this example, then the page 2, I'm going to ask you to do a quadratic model and a piecewise model. So the coding then is going to be specific to what you're working on. It's a 2-piece model in your homework, as well as a quadratic effective age. Or not age, it's enthusiasm for mini golf. So let's look at that. So the quadratic model first. The only thing I had to do, I'll come back to this when it's relevant. The only thing I had to do for that is to create a centered version of age. So age is the predictor for which we had a quadratic effect on income. I had picked 18 as a centering point. Would reviewer 3 want to argue with me about that? Of course. Of course. What's my comeback? Why did I center it in the first place?
They don't really have much of an income because they're technically living with their families.
What does centering age at 18 so that age 18 is my new 0 in the predictor do?
Makes 0 mean something.
Makes 0 mean something, and why does that matter? What changes as a function of where 0 is? Not the slope, the other one.
The intercept.
Intercept, yeah. What would happen to my model significance, my R square, etc., if I picked 20 instead of 18? Nothing. So there's no wrong way to center, only weird. What if I had left it uncentered? then it'd be the predicted income for a newborn baby. That's what your intercept would be, right? Is weird, it's not wrong. I mean, the line just keeps going, right? So the choice of centering is somewhat arbitrary. It's used for interpretation purposes. So in this case, I picked 18. So there's my distribution of age. So reasonably continuous. This is the code by which I got the plots. I'm not asking you to do any of this. This is sort of advanced stuff, but I wanted to show it to you. So this is the plot of age on the left that we're going to be fitting a quadratic trend through. Because it looks awfully quadratic, albeit with some noise on the upper end here that I don't know how to account for. And then these are the piecewise examples to follow. So let's do age first. So I ran a model that had a linear age by itself just to show you what happens. I'm not asking you to do this in your homework, but because you've already done it before, but I wanted to show you what happens to the coefficients. So age 18 as its only effect. So here is an instance in which I have one single predictor for the model. So 5.52, the t-value for that slope, squared, is my f of 30. So degrees of freedom numerator for the model is 1, because the model has one fixed slope. So I know from the significance of this fixed slope that my model has significantly accounted for variance in income. One fixed slope, then that is what R squared means. It's accounted for 4%. It's a small slope, but we have a lot of people, so it's significant. So it's trying to fit a straight line through this. It looks like the straight line is slightly positive. Most of the people are on the younger side of age, and so it's kind of like that, what it's trying to do. So what do the results mean then? These two numbers are my two fixed effects. The intercept of $12,000 is the expected income for an 18-year-old, not a newborn, not unless they have a college fund or something. And for every year older you are, what happens to your income? $206 up or down? Up per year, right? Significantly. So I would say the slope is significantly positive. $206 per year increase in income. That tendency of income to be linearly related to age explains 4% of the variance in income, which is significant. I can say it's significant because T is significant or because F is significant. It's the same thing. And two different versions of R squared, reduction in variance due to the predictors I've included, or correlation squared between y hat and y. And the correlation between age and income would also be R in this case, the standardized slope. Now, adding the quadratic. You can do it directly in either program, so long as you're in GLM and SAS or regress in Stata. In SAS, and this star means an interaction term. So it's the effect of age times age, which is the quadratic. In Stata, here, I'll see how young these people are. What is this thing called? It's a pound sign. You surprised me. What is this thing called to anybody under 40? Hashtag. Yes, hashtag/pound sign. The great divider, right? So it's hashtag/pound here in Stata or star in this. Stata, by the way, this C dot just denotes that the predictors are being treated as continuous. I got in the habit of putting that in a while ago, and so that's why it's in there. I believe that's a default. So I don't think you should need that, but I have it in there to contrast it with other things.
I've been running into some problems. Output out equals work pred income by age, right up there.
Mhm.
That's not something we change, is it? What does that actually mean?
So this is how I made the pictures. So what this does actually is create a new data set in the work library called Pred Income by Age. That's the name of the data set, and I named it according to what the model was supposed to be doing. It's saving a column of predicted values that I've named y hat for age, and it's saving the standard error of those predictions. And I used that to make this picture with the fitted line through it to show you how the model predicted what income should be relative to what the original means per each unique value of age were. So you do not have to do that I'm not asking for any pictures as part of your homework, but I wanted you to have the code as to how I got them, just for future reference. Okay. So these extra things are illustrating the trend of the quadratic effect. I'm not going to ask you for those either because that's sort of an advanced topic, but I do want you to see what happens to the coefficients. So the three coefficients from the model here, if I were to label these, this is beta 0. What's this one? Beta 1. And what's this thing? What comes after 1? 2. Yeah. So yeah, this is me being nice. This is Proc Lisa. And the reason I have a job is because they don't label things for you like this or put them in equations. So intercept. You all know the definition of the intercept as the expected outcome when all the x's are 0. So what does it mean in this context? Expected income for what kind of person? $18 still, right? Now why is it $2,000 and not $12,000 like it used to be? It has to do with what expected means, right? So the definition of the intercept is still the predicted outcome for an 18-year-old. That hasn't changed because we haven't added any other predictors by which to make it conditional. But expected. Previously, it was expected from a straight line. Now it's predicted or expected from a bendy line, the curve. So if I had a straight line trying to fit this versus a curved line, the straight line thought the intercept should be up at $12,000. The curved line thinks it should be down here at $2,000. So expected has changed. Likewise, it used to be $206 a year more per your age. Now it's $1,200 more. Now that changed because it means something different. Because of this quadratic term, this is the linear slope at 18 specifically. I got to get out my my little stick here for this one. It's good for waking people up or doing calculus. It's the linear slope at age 18, the slope of the line that's tangent to the curve at that point. Instantaneous linear slope is what they say in physics. Now, what does my model say is going to happen to it as age goes on? It's one of 4 kinds. Remember what they are? More positive, less positive, more negative, or less negative. So it is this. Start out positive. What's happening to it? Less positive. Yeah, and eventually heading into negative.
More negative.
Eventually, yeah, but less positive to start with, sort of as the reference point in the model. it becomes less positive, homework question, by twice the quadratic coefficient. Twice. So this is 0.02, it would be by 0.04 per year of age. And so
Okay,
the,
it's less positive by twice the quadratic.
yes, that's how you do quadratics. This linear slope of 1.2, which is at 18 specifically, becomes less positive by twice the quadratic coefficient per year of age. So I have given you some additional calculations here, estimates that I requested. Predicted income at various ages as well as predicted linear slopes at various ages. So the model gives you predicted income at 18 and the linear slope at 18 directly. Anything else is our friend the linear combination. So I asked for the predicted income at age 30, at age 50, and at age 70. The way that I got that is by saying I need one beta 0. I need a beta 1 multiplied by how many years since 18 it's been. And then I need a beta 2 multiplied by how many years since 18 it's been squared. Yep. 12 squared is 144, 32 squared is 1024, and 52 squared is 2704. And yes, I had to look those up. I'm not a savant. Other than 144, I had that one. But likewise, the model tells me that the linear slope for age changes by twice the quadratic per unit age. So I can figure out what the linear slope would be at any age by starting with beta 1, the linear slope itself, and adding to it twice whatever year of age I want. So for age 30, that's 12 years times 2. For age 50, that's 32 years times 2. And for age 70, that's 52 years times 2. And that's what gave me these numbers down here. So at age 30, the linear slope is still significantly positive. So we know from the model parameters, let me find that, where did it go? Here it is. The linear slope at 18 is significantly positive. The quadratic is making it less positive. At age 30, it's still positive. By the time it hits age 50, it's non-significant. And you can actually work out the point at which the slope goes straight to 0. The formula for that is in your slides, in case you want to know. And then it starts to become significantly negative after that point by age 70. So in this case, F and T summary of the model up top. Two slopes working together to describe the effect of age. So age as a concept is sort of one predictor variable, but it takes two slopes to describe it, a linear and a quadratic effect. Those two slopes together account for significant variance in the outcome. I know it's significantly greater than 0. How much is it? What do I look at? R square, yes. 11%. So yeah, the F is testing simultaneously whether these linear and quadratic slopes are different than 0. It's doing that by accounting for their own standard errors as well as the covariation between them in the standard errors. So that's not something that's easy to do by hand, but fortunately we don't have to. And then here's the pictures that I made. as well as the one that came, the one on the left came by default, the one on the right I made with the extra pieces of code. Okay, how are we doing? Yeah. All right, cool. Piecewise. We talked about this last time, but just to show you it implemented in the code, going back to the beginning, where I made my variables here. So in this case, I wanted to fit a 3-piece model to describe the effect of education on income. Based on the trends in the data, I hypothesized one slope for any education level that is under high school, so stopping at 11, a bump in your income going from 11 to 12, and then another slope that describes the change in income after 12. So the centering point for this model is when people are 11. So when someone has 11 years of education, that is when all 3 of my slopes would be 0. When I get to 12, I pick up this bump. And then after 12, I retain this bump for being a high school graduate. And then I pick up the effect of years past 12 via this slope. So in your homework, I'm only asking for 2, not 3. So it'll be a little bit simpler. Okay. And we can talk more about this next time as well if it's confusing. So does the idea make sense? We're sort of, it's sectioning up the variable. And we're looking at the change during each section. And how to make the sections is entirely up to you. You have to know that a priori as a way of testing your hypothesis. I did it based on a combination of inspecting the data and logically thinking what would happen.
Can you real quick explain, okay, so else if, and you do the last one where
Yeah.
you do the minus 12, that's like the centering variable.
Yeah, let me find that again.
So can you just like talk through what that
sorry.
meant in your brain?
Scroll too far. Yes. No, come on. Here we go. There we are. Found it. Yes. So the else if part, is that it?
Yeah, just that 12. So I see if your education is greater than 12th grade, then you get this bump. But then the over high school, because I tried to do your little thing and your challenge, and I got a little lost right around this area. So like that 12 over high school, I don't understand like why that's negative.
Because I want to know how many years past 12 you have. So essentially your model is making up new reference points as it goes along. So 11 is the intercept. The first slope is going to keep track of years until 11. And then if you're over 11, it shuts off. Right? It's not relevant anymore. It's done. Then, if to go from 11 to 12, that's this one. And then it's done. Basically, you hold it constant. And then you pick up from 12 on, how far past 12?
So it's not minus, it's like when we center.
It is. It's centering because it's making like a new jumping off point for each slope to start. Yeah. Did anybody else try the challenge? Did you? No? No one did? Okay. Well, I haven't done it. I wanted to save it for you to see if it would work. So let me get the results from that model. So I put in all 3 slopes at the same time because they work together to describe the overall effect of education. So I know from this part that we did account for significant variance in income via my 3 slopes. Here's my R-square. And here they are. So again, this is beta 0. This is beta 1, beta 2, beta 3. Okay. So the intercept. Expected outcome when all the predictors are 0. Based on my coding scheme, that is grade 11. That is when everything zeroes out that I made. So $8,500. So starting from 2 to 11, that's the range of education this first slope is covering. What happens to your income for every year more educated you get from 2 to 11? It goes down, but is it significantly down or non-significantly down? And how do I make that decision? P-value, right? What's our cutoff for P? 0.05, because that's what the world says. So the fact that this is greater than 0.05 means what? It's not significant. Not significant. Think back to the distribution, right? Are we in the tails or are we in the middle? We're in the middle. We're in the expected variation.
Can I ask a question?
Yeah.
So if it's 0.5, then it wouldn't have been.
It has to be less than 0.05. So if it was 0.05 exactly, it would be non-significant.
And this is not significant.
It is non-significant because it is, it's greater than 0.05. 0.05 or greater is non-significant. Yes. Meaning that it would be expected, a test statistic this extreme of this value would be expected like 65% of the time. So no big deal. If the null hypothesis were true, this is an expected fluctuation around 0. That's what it means. In contrast, these two, so grad high school is the difference between 11 and 12. So people who graduate high school have a bump, $4,000 and some odd dollars. And from there, for every year past high school, every year of education gets you $2,000 more dollars. However, the challenge was based on the idea that this slope from 12 on doesn't look like it fits very well. And I had suggesting replacing it with 3 more slopes instead. So we wanted to try that. Okay. One question that I'm going to ask for on your homework that is not in this example, but I'm looking to see if you can extrapolate, is how to test whether or not these slopes are different from each other. So I'll let you percolate on that. You can ask me questions if you want, but that's one extra thing I'm asking you to try and do, because you know how to do it, you just don't know that you know. So, all right, so we are out of time. Questions? Yes.
So the first page of part 2, I wonder if it's for the piecewise you just compare 3 to 4 and 4 to 5, 5 to 6 instead of 2 to 3 to 4 to 5.
Yeah, we haven't looked at that one yet. Are you saying there's a typo in it? Or
I just want page 7.
page 7? This one?
Yeah, here. It's H3V4, H4V5. It's different from the general model, which is 2 to 3, 2 to 4 to 5.
This is a different way of coding the variable. So we haven't talked about this one yet, but I'm not asking you to do it. So this is just another example that we're going to go over. Okay. All right. Then office hours later today if anybody needs me. Otherwise, I will see you Thursday.